start to talk a little bit about some of the first volume visualization methods that we can use. Now, there are kind of we can classify the volume visualization methods into two styles or two ways or two groups if we want to. One's called indirect and one's called direct. You'll notice indirect and indirect and direct. Indirect methods includes isosurfacing slicing, MPR, multiplanar reconstruction, that is more than one slice, or surface fitting methods such as marching cubes and marching tetrahedra. And in those, what that means is to compute those planes and surfaces, they rely on interpolation of data samples. So instead of looking at the data samples directly, we're looking at interpolated data samples between the originals. So that's why it's called indirect. And direct methods don't rely on interpolated samples, but you see the samples and use them directly as opposed to always interpolating all the data samples. And we have a special, we're going to talk about slicing today. We have a special lecture for marching cubes, another special lecture for ray casting, shear warp factorization. We don't have special lectures for splatting and 3D texture mapping just because of time constraints. But that's just to give you a little preview. We can also classify methods not only by indirect and direct, but we can classify them as image-based or object order-based. When you see the word image, you think of a 2D plane, like the projection onto this wall, because that's ultimately what we are seeing. We're seeing a computer monitor or a projector, which is a 2D image. And algorithms that operate primarily in that space are called image order algorithms, or they're outer processing loop. So an image order algorithm has a processing logic that starts like this. For every pixel, do some operation. Remember, pixel is a picture element in 2D. So you can imagine having pixels and then computing color and opacity for every pixel on the screen, for example. And the computing time is related to the size of the image. So the bigger the image or the higher the resolution of the image, the more time it takes to compute. And we're going to discuss a technique, an image order technique called ray casting. Now, the one that's less familiar to you is called an object order technique, and in that case, we go into 3 dimensions, or object space, or volumetric space, and the outer processing loop looks like this. For every object or voxel, perform some operation. So instead of traversing image space, we're traversing object space. Object space is another way of saying 3D space or volumetric space. And the performance time is related to the number of voxels, or the number of cubes in 3D, as opposed to the number of pixels in image space. And we're going to talk about an object order technique called marching cubes. One is called splatting. We don't really talk about that, but we do talk about one called marching cubes, which is a well-known volume visualization technique. Any attendance register flying around? Did everybody sign it?
My name wasn't on it, sorry.
Oh, okay. So
I came onto the module like last week.
Okay.
My name's not on mine.
It's not? Okay. Make sure you watch the previous lectures on the YouTube channel, otherwise you're going to be very, very lost. Here is that, like a picture of that idea, the image order processing. you can see an image on the left here. I guess I can't really reach up that high. You can see an image on the left. The person, the viewer, is over here, is not shown in the image. So the person is here, looking that way. There's the image, and these little squares are pixels. And emanating from those pixels is a ray, and the ray cuts through the volume data or object space. So basically the ray traverses the volume space from front to back in this image and computes a color and opacity for every pixel. That's why it's called an image order algorithm. So there's a loop that says, you know, for every pixel in image space, cast a ray into the volume and compute the color and opacity. And so it's like a rasterized approach to computing an image. By the way, does that term ring a bell to anybody? Ray casting? Where have you heard that term before? And what's your name? Corey. Are you sure you heard the word ray casting, or was it something just very similar?
Ray tracing.
Ray tracing, exactly. Yes. They're not the same, and we will talk about the differences, but they have some things in common, and they are related to one another. So ray tracing, we would call that an image order technique. That we would call that in this data viz module. That's probably not how it was described in the computer graphics module, but that's how we would call it here. And then in the other classification, we have object order approaches, so they traverse the volume and project to the image plane. So imagine traversing the volume voxel by voxel or cell by cell, and then running some computation. For example, what influence does this data have on the color and opacity of the pixels, the corresponding pixels in the image plane? So it's almost like the inverse. One's from left to right and one's from right to left. Or it's better to say one's from image space to object space and the other one is from object space to image space. So we just went over the Volviz pipeline, indirect versus direct terminology, and then object order versus image order terminology. There's lots of new terminology in the introductory parts of the lectures. So these are some volume viz techniques that you would imagine by yourself, so to speak. You won't need necessarily a module to imagine these, and probably you've seen them in some way, shape, or form already, perhaps. So slicing was in the video we saw earlier today. There was this clipping cube. So you can imagine a volume and then just taking a slice through the volume and projecting the data onto the slice and then looking at it. So an axis-aligned slice just means that the slice is aligned with one of the axes, like one of the planes, like the XY. This would be the XZ plane, this would be the YZ plane, and this would be the XY plane from my perspective. So the slice is aligned with one of those planes. The data can be sampled on regular grids. No transfer function, no color is necessary, and we can use windowing or color contrast enhancement. Slicing through arbitrary grids and at arbitrary angles is not as easy, and it requires more interpolation. Can anybody imagine what this image is here? Anybody feeling imaginative today, feeling like they could imagine what that is. I won't tell you. I'll just maybe we call on somebody. Name, please.
Dan, by the way.
Dan.
Yeah, and somebody's punching a hole in basically like punching a hole in something.
Punching a hole in something. Oh, you mean like this cylindrical object punching a hole into a surface?
Yeah, I guess so. Yeah.
I suppose so. I suppose so. What we're seeing, this is a cylinder, and what we're seeing is a slice here. This orange sort of plane is a slice, so that's an example of slicing. And it's a slice through a flow data set, actually. So this is a cylinder, and then there's fluid flow moving from this side of the cylinder to the other side. And somebody has decided to use a slice to visualize the flow in this plane. And they're using streamlines to visualize the flow past the cylinder as well. And then velocity magnitude, the speed of the flow, is mapped to color. So that means blue, dark blue, for example, is slow moving flow. And then the more quicker moving flow is the more orange or red it is. Right? This is slow. The green is middle velocity or medium velocity, and then the higher velocity is the orange. And actually that same color map is used along the surface of the cylinder as well. So the fast moving flow is the flow that's hitting the cylinder from this side, and then it wraps around the cylinder and gets slower due to friction generally. And then, yeah. So that's just an example of slicing, but it also happens to be a flow-viz example. Here's another example of slicing. Oh, I think I have, let me just see if I have, this doesn't work in the PowerPoint version. Let's see if I'm sorry, the PDF version. Let's just see if that animation, that's actually an animation. Okay, that's not working either. I'll go back and then I'll show an example at the end. Now, another early volume visualization example, this is an early one. So representing, that's the famous teapot that everybody knows and loves, right, from computer graphics. That's like your first data set that you ever render in computer graphics. And that's usually represented by a set of triangles, as probably you guys have all seen from computer graphics. Here's the teapot represented as a set of cubes. So somebody said, oh, let's try representing that same surface with a set of cubes, and then see what it looks like. And this is an example, and it doesn't look as nice as the one rendered with triangles. But whoever thought of this was clever, because when we look at the triangulated version of the teapot, it looks quite smooth, doesn't it? But when you render those triangles onto image space, you're actually looking at squares. Pixels are squares. So if the squares are small enough, they generate a smooth image, which is not very intuitive. But they have to reach the limits of human perception, basically. So the human perception or the visual system acuity has limits. So when those pixels get small enough, you cannot perceive that they're squares anymore. They look like they can convey smooth imagery. Well, the same thing is true about cubes. When those cubes get small enough, you can create smooth-looking surfaces with them, which is the surprise. So this is an early version that shows artifacts, aliasing artifacts due to the big cubes. But if they get small enough, you can create a smooth-looking surface in an image. And those are some examples, for example, of smooth images or smoother images and surfaces created by reducing the size of the cubes to something that's hard to perceive with the human visual system. And this is resulting in something called aliasing, like those ragged staircase artifacts. Aliasing, here's, if I look up the word aliasing in the like the OpenGL programming guide, or one of our favorite computer graphics books, it will say a rendering technique that assigns to pixels the color of the primitive being rendered regardless of whether that primitive covers all or only a portion of the pixel's area. This results in jagged edges or jaggies. Another way of saying that is the data is sampled at a resolution that's very low or undersampled, and then your eye can perceive the undersampling. Anti-aliasing is a rendering technique that assigns pixel colors based on the fraction of the pixel's area that's covered by the primitive being rendered. Anti-alias rendering reduces or eliminates the jaggies that result from alias rendering from the same book. And in that previous example, we can shrink the cubes down to a limit that's not perceivable by the human visual system. And that's anti-aliasing. What you could say it's anti-aliasing, but it's also just sampling the data at a higher resolution so you don't notice the undersampling artifacts. And now I'm going to show another example, because I like examples. Wait a second. Here's a volume visualization. And at some point, there will be some slicing going on. I can't remember when, but you can imagine that this is the soft tissue of a brain, and that's volume data. And then the question is, how do you visualize the different subsets of that volume data? And the user is changing the rendering parameters to see different subsets of the soft tissue in the brain. So they have a rendering parameter, okay, and that's taking a slice through the 3D volume. That's one of the reasons I included this example, is because it shows what happens when you take a slice through the 3D brain. And you can project different images and different subsets of the data onto the slice. They have some controls for the brain's gray matter, the brain white matter, and other soft in the fluid, brain fluid. So they have special color and opacity assignments for each 3 of those subsets in the brain data set, so that the user can focus on different subsets. And it's a nice illustration of, I just like this illustration for the slicing aspect. That's one of the reasons I like it. But it's also just a nice example of what does volume visualization look like, and so on. And Surprise, surprise, there is a copy of that on the YouTube channel, module YouTube channel, if you want to look at it in more detail. Any questions on the introduction to volume visualization? I do have at the end, if you're interested in further reading, this is a good book chapter to read. The chapter 10 of the Data Visualization Principles and Practice book. That's a good chapter to get an introduction to the topic.